Hi everyone, this is Dr. Hammond for Physics 3210 Electromagnetic Waves at the University of Windsor. Um, we've already covered relativistic dynamics and relativistic mechanics, and this was your daily assignment for today, Thursday, March 26th. As we saw, Newton's laws still hold in relativistic mechanics. However, you just have to redefine exactly what you mean by these forces and these momenta. But this example 1210 discusses what happens when you have motion under a constant force. So we're going to start at t equals 0. We're going to have no motion at t equals 0 to simplify the math. And so in this case, we get that the momentum under constant force is going to be force times time plus some constant. Well, of course, this constant is going to be 0 at t equals 0. So using the equations that we went over in the previous tutorial, the momentum is going to be force times time, but that's going to be mu over 1 minus u squared over c squared. And so if we solve for u, then that means that the velocity as a function of time is this force over the mass, or I guess this kind of classical acceleration, times time over the square root of 1 plus force times time over mc, and then all of that is squared. So of course, if c were infinite, or our velocity is much slower than the speed of light, then we don't have this denominator. This is effectively kind of like a gamma. And so our velocity is just force over mass times time, and that's exactly what we expect. However, as we approach the speed of light, we obviously can't ever exceed the speed of light, so we need to have this velocity, this rate of change of the velocity has to slow down, and so there has to be something that limits that. And so that's what this denominator does. That as our time goes to infinity, this thing approaches c. So if we look over here, here are two plots. One is time on the x-axis, velocity on the y-axis, and if you just had that non-relativistic acceleration, then you would be following this orange line here, and so you would just speed up indefinitely. But if we take this denominator into account, then this ends up plateauing, and this limits, at the speed of light, which is 2.9979 times 10 to the 8, so, or 3 times 10 to the 8, thereabouts. And so you can see that this thing ends up approaching that, but never actually reaching that. So this time here, 1.6 times 10 to the 8, is actually 5 years. So what I'm thinking is, if we're on a spaceship that accelerates at g, so 9.81 meters per second squared, and this thing we're accelerating, in order to, simulate gravity on Earth, and this thing we're flying through space, or interstellar space, I guess, then after 5 years, we would be pretty close to the speed of light. It would be something like 98% the speed of light. But after 1 year, which is about 3.15 times 10 to the 7 is here, we would be right at around the speed of light if we didn't have this relativistic correction factor, if there wasn't this limit that we couldn't travel faster than the speed of light. But there is that limit, and so instead we're down here about 2 times 10 to the 8 meters per second, which is about 2/3 the speed of light. So after 1 year traveling at g, you end up, or accelerating at g, you end up at about 2/3 the speed of light. What I thought was kind of interesting, though, is, this is kind of expected, that you can't go faster than the speed of light, and so this is just going to plateau to that value, and this is going to be the curve that it takes. What I thought was kind of interesting, though, is actually if you plot this ordinary velocity versus proper time, so that would be the time that you would feel in that spaceship, and if you constantly accelerated at the speed at this acceleration g, it turns out that it actually takes you about a year. So as I said, 3.15 times 10 to the 7 is number of seconds in 1 year. It turns out that if you accelerate at g, 9.81 meters per second squared, that you the the proper time ends up compensating for this gamma factor here, and so this actually just linearly increases. But of course, you can't go faster than the speed of light, you never can, but it turns out that your proper time also decreases, and so you slowly approach the speed of light, but your time also slows down, and it turns out while accelerating at g, it takes you about a year, and then eventually you just don't see any more time ticking. The coincidence is that g is 9.81 meters per second squared. If it were 10 meters per second squared, this would take 2.9979 times 10 to the 7 seconds, which is about a year, 3.15 times 10 to the 7 seconds. So it's just a coincidence, but it's kind of funny that if you left, today, Thursday, March 26th, 2020, and you accelerated at g in the spaceship, you would never see March 26th, 2021, or I guess never at the same time. You'd still see March 26th, but I guess you wouldn't see, noon the next day, or the next year, which I thought was kind of funny. Just kind of a neat coincidence. Anyways, this is the daily assignment for today for you to understand this and look at this and see what happens as you accelerate and show that you can't accelerate indefinitely. Well, I guess you can accelerate indefinitely, but you can't keep on increasing your velocity indefinitely because, of course, you have this upper limit of the speed of light. All right, and that's it for this daily assignment. On Tuesday, we'll be talking about relativistic electrodynamics.